Okay, so I believe this is the last video lecture of this chapter. All right, so we left off and I was talking about the peripheral nervous system. The key takeaways from this slide is really to understand the difference between the sympathetic and the parasympathetic. That the sympathetic is fast. It's the fight or flight, fight, flight, or freeze is actually the way we're talking about it now. And the parasympathetic is the one that slows things down. It's implicated in rest and digesting and healing. When we're under a lot of stress, we often don't heal very well. We age faster, and that is partly because we put a lot of pressure on the parasympathetic system isn't able to keep up. Right. Right. So another thing that happens when we're under this fight, flight, or freeze is like we may get nauseous. We stop digesting. Sometimes people will throw up. They may wet themselves. They may poop their pants when you get scared enough. And that has to do with the sympathetic system wants to like lighten its load. So because it's under this fight or flight model, it wants to get the heck out of there. And now is not the time to ovulate. Now is not the time to digest. Now is the time to run. But then that is the sort of the opposite of what the parasympathetic system does. Okay, so then we have this. I spoke about the parietal lobe as it being kind of a strip, right? Remember we have the occipital in the back. That's a quiz question. Why do you see spots? When you hit the back of your head, it's because it's shaken up that occipital lobe. We have the temporals over the ears, and the left is the language. We have the frontal lobe, which plans ahead, right? It thinks ahead for us. But right in the middle, somewhere towards the back, well, there you go, you can see it right there, is a parietal lobe. And along that, there's a strip called the somasensory cortex. There's a somasensory one for receiving sensation, receiving sensory input, and there's a one for sending sending a motor for sending things back out. And oh my God, homunculus, that's his name. I was like, oh my gosh, I can't remember this guy's name. The space dedicated to receiving sensory information from our body is not proportionate to the size of those organs. In other words, and that's what homunculus sort of represents here. If you've ever bitten your lip or maybe gotten something in your eye or have a hangnail and you know how much that hurts, right? It's this little bitty hangnail. It's this little bitty splinter. How come it hurts so much? Well, the reason it hurts so much is because there's relatively a lot, there's a density of nerve endings. Well, all those nerve endings have to be processed in the brain. And that means it takes up a lot of brain space to process that information. And that's what is illustrated in the somosensory map. And what homunculus is intended to illustrate is if our senses were proportionate to our body shape, to our body size, right? This is what we would look like. We would have very large hands because there's a lot of and that's a lot of space in our brain dedicated to receiving information from that part of our body. So along this strip, if you go from, I don't know, about here, I hope you can see it, all the way up to say here, that's a lot of brain space dedicated to receiving information about our hands. The same thing with our tongue, right? If you bite your tongue, dang, you can hardly see it, but it hurts like the dickens because there's a lot of brain space dedicated to their senses on our tongue. And in some cases, like I kind of mentioned before, how these regions of our brain are not like puzzle pieces and they can't be pulled out. There may be some crossover, and this is a little R-rated, so I hope you're all grown-ups here. But I find it interesting that the feet and the genitals happen to be kind of right next to each other because this is a very common culture fetish, right? A feet fetish. And so I wondered if that doesn't explain it, is that in our brain, our feet and our genitals happen to be, the sensory input from them happen to be processed in the same space. That how those, and then of course you have your back, right? If you ever had that activity where people put fingers on your back and you try to figure out how many you can feel, and we can't because there's not what does it say on here? There's not very much space, relative space dedicated to your back. So that's your somosensory cortex. And we got another concept. Another really important concept here is the idea of plasticity. And plasticity means, if you think about plasticity versus steel, right? Plastic is malleable and it can change. Steel does not, right? It is not flexible. So it is said that the brain is plastic. And what that means is the brain is shapeable. And there's two kinds. It's shapeable, it's changed. Or we can mold. It can be influenced. It can be shaped. It can be both. It's both functionally plastic, which means the functions in one part of the brain. If that part of the brain gets damaged, those functions can shift to another part of the brain. When my mother's partner had a stroke, the doctor told him to keep reading because some of those functions from the damaged part of the brain would shift to another part of the brain. So it's functionally plastic, but it's also structurally plastic. And what that means is the structures of the brain change shape. One of the most obvious examples is neurogenesis, that we know the birth of new brain cells. But other examples show up in some of the research on like depression and post-traumatic stress. One illustration is that obese people have fewer dopamine receptors than do not obese people, or there's some evidence that suggests that post-traumatic stress, that the amygdala, you remember that's the fear and anger, that the amygdala is actually smaller in people that have post-traumatic stress. I'm trying to think about the one, depression. I believe it's the same thing. Does it get smaller? Does the hippocampus get smaller? But anyway, the point is that our brain, there is some evidence that external experiences or our experiences will change the shapes of our brain. There we go. It says right there, experience sculpt brain structures, and even the phenomena that I spoke about earlier, which was pruning, right? That if you use these parts of your brain, they won't be pruned, but if you don't use them, they will be pruned. Okay, and then finally we get to only one slide on the endocrine system. The quiz question is, what do endocrinologists study? Endocrinologists study the endocrines, hormones. The answer endocrines won't get you the point. You need to say hormones. And the hormones are regulated. Hormones are like neurotransmitters. They are chemicals, except instead of being in our brain, between our synapses, they are in our blood. And they move a little bit slower, right? So our glands are regulated by our that one right there, hypothalamus. I've been talking to myself for a long time. By the hypothalamus, which is part of our autonomic, which is our automatic nervous system. This is beyond our control, right? And there's also a little structure in our brain and above our adrenal glands, but these things happen without our conscious awareness. So we can't really, I can't tell my pituitary gland, that it needs to. In some cases, these glands may actually may act on other glands, which then cause the release of hormones. Some important hormones that we've already talked a little bit about. You've heard some of these words. Oxytocin. Maybe we haven't talked about oxytocin. That's a really important one. Oxytocin is often called the cuddle hormone. This is implicated in bonding and trust. Women have more oxytocin than men. If you've been in some of my other classes, you've heard me talk about them before. Oxytocin, we see spikes in oxytocin in women, and under hugs can increase your oxytocin, but 3 of them also are during childbirth, during labor and delivery, during breastfeeding, and during orgasm, interestingly enough. So I always like to say something like when you just love somebody so much, you just that's oxytocin working for you. It's really what helps mamas and daddies, but moms got more of it, to just fall in love with their baby and carry that baby around with them wherever they go, golly. Endorphins, we've talked about that one already. Epinephrine and adrenaline, these are excitatory. These are part of the stress response. Norepinephrine is also part of the stress response. And then testosterone, which interestingly men have more of. Women have testosterone too. Men have oxytocin and estrogen, but testosterone is implicated in aggression. There's some really interesting research on how you can increase how you can increase the level of testosterone in somebody's blood simply by being aggressive, causes their testosterone levels to go up. And then The last slide or this last idea is really about genetic vulnerability. So one of the big questions in psychology, actually in all social sciences, I think, is the relationship between nature and nurture. There's lots of interesting research on, is happiness genetic? The idea is that our brain is an organ, right? It's a biological structure. If our biological structures are influenced by, like, if we inherit our height or our hair color from our parents, is it possible or isn't it possible for us to also inherit the brain structures, right, from our parents? So if our parents, say, struggle with producing enough dopamine, is it also logical to assume that their offspring could potentially have the same genetic vulnerability? This is why we see some disorders, some emotional disorders, some addictive behaviors running in families, because we can pass along these biological, what's often called biological predispositions or genetic vulnerability, right? But let me just caution. So if our parents have these conditions, we're probably at a greater likelihood to have these conditions, but it does not guarantee we will have them. Our parents can be very tall and us not be very tall, right? These are not guarantees, but I think it is worth considering that, like, here's an example, alcoholism, right? I have come to the awareness that addictions run in my families, but my mother never drank alcohol. I've never seen my mother drink alcohol. So we cannot become an alcoholic if we're never exposed to alcohol, but she is addicted to food. I also know that when my mother struggled with anxiety and depression, I found, and I also struggled with it, I started with the same prescription that she did because I knew it was helpful for her brain. Now, this does not mean that again, this is the thing I really want to end this with, and I've gone over my time, is genetic vulnerability does not mean predisposition. It just means risk, and we should attend to that or be aware. Okay, I hope I've covered everything. This has been a long chapter. Thank you for listening.